Okay, this lesson is on distance, velocity, and acceleration. We're calling this part 1 because we will revisit this relationship once we have done antiderivatives and integrals and come back and do some more with it. For today, the main thing that I want you to get is this relationship between distance and velocity and acceleration. So, distance, I want you to think of it like it's the original. That's why I'm calling it f. Velocity is the derivative, and acceleration is the second derivative. And when we did the car out in the hallway and did the car experiment, we did the graph of the distance over time, and we talked about the velocity at the specific points on the graph, and we were developing that relationship then. But the distance is the original, velocity is the derivative, and acceleration is the second derivative. Other things that you need to know right now is, what is velocity? Well, velocity is a measure of how fast something is moving and what direction it's moving in. Although we don't talk about direction as much in this class as we do in, say, a physics class, it is factored into velocity. The units for velocity are things like feet per minute, meters per second, miles per hour, stuff that is measured in distance over things that are measured in time. That is the units for our velocity. Something else that comes up is speed. Speed, I'm saying, is the absolute value of velocity because it's just the amount, the speed that you're going, how fast you're going. Direction is not factored in. A negative velocity would mean like going left or going down. Things that we put a negative in front of kind of make sense directionally. It doesn't mean your car is going to show up on your speedometer as a negative amount. Your car would show up as a positive amount. And so that would be registering the speed. That's why it's called a speedometer. So speed is the absolute value of velocity, and that will come into play again when we visit free response questions once we've done both parts of this subject. Acceleration is how fast something is speeding up or slowing down. We're just using that same word for both. Sometimes, you can say deceleration, but in this class we generally just use the word acceleration to talk about either one. Positive meaning that it's speeding up, and negative meaning that it's slowing down. Excuse me, not positive meaning speeding up and negative slowing down. Sorry. The direction also occurs here. Sorry. Positive meaning upward, and negative meaning coming down. So when I'm talking about acceleration due to gravity here, I'm giving you the values in meters per second and feet per second that we use in this class. Acceleration due to gravity is negative because the objects are falling down toward the earth, and that would be what I was referencing up here and kind of botched. Okay, again, our acceleration due to gravities are constantly changing velocities by 9.8 meters per second squared or 32 feet per second squared. Those will be a constant thing if an object is in free fall. Okay, so let's get to some examples. Our first example is a student throwing a ball off of a roof so that the distance equation is S of t equals negative 16t squared plus 30t plus 100. A lot of times you are going to see S instead of D for distance because we use D for so many other things. So S is typically what will stand for distance or sometimes displacement of an object. And so the question is, when does it hit the ground? Well, what do you know when it hits the ground? You know that the distance off of the ground is 0. So when it hits the ground is when the S of t equation is going to equal 0. So I'm going to take that negative 16t squared plus 30t plus 100, and I'm going to set that equal to 0. And since this is a quadratic, I have options. It may factor. you can use the quadratic formula, or in our case, what I'm going to have you do is just graph it and find the zeros. And so obviously it's an upside down parabola. We're just finding where it crosses the x-axis. One answer will make sense, one will not. And if you type that in and graph it and calculate your zeros, you get time to be 3.608 seconds. So they threw it off the roof. It took 3.6 seconds to hit. And you want to make sure you're rounding correctly to 3 decimal places if you are using that calculate the zeros thing. Now, the question, part B, makes us work a little bit harder. It says, how fast is it going when it hits? Well, how fast has to do with velocity. And so let's first find our velocity equation. And as we said in the beginning, the relationship between distance and velocity, velocity is the derivative of distance. So I'm going to take that derivative of our S equation. And I'm going to get negative 32t plus 30. So the derivative of the S equation is this equation here. And we want to know that velocity when it hits. Well, we know when it hits, we just found that. It hits at 3.608 seconds. So we're going to take the velocity and plug in 3.608. So negative 32 times 3.608 plus 30 gives us negative 85.456. And then you have to think about units. This equation, since the negative 16t squared became a negative 32, we're going to go with that's in feet. So this is feet per second. Because if we were in meters, we would be looking at 9.8s and 19 point things. 19.4s, I think. So I can recognize by the 16t squared and the 32 that we are in the feet as my units. Okay, our second example, we have Miss Taylor driving on a road, and her distance equation is given by S of t equals 2t squared plus 5t plus 10. Now, the 9.8 or 32 feet per second squared is not going to come into play in this because this is not an object that is dropping. This is a person who is driving on a road, and their velocity and acceleration is directly tied to how much they're pushing their gas pedal, not to gravity. So our answers here will be not factoring in any gravity. So this is her distance equation. We want to know her velocity at time 5. And so the velocity equation, again, is the derivative of the distance equation. So we would get 4t plus 5. Her velocity at that time, we would just have to plug the 5 in. So 4 times 5 plus 5 gets us 25, and we'll assume she's driving in miles per hour because that's what we're used to. So she's on some really slow road. Second question is, what is her acceleration at time 10? Now, if this were talking about a book that had been dropped or something that had been thrown into the air, the acceleration at any time would be the same. It would either be the negative 9.8 or the negative 32. But since we're in a car, this situation, we'd have to take the second derivative. So the derivative of the velocity will be the acceleration, and that is just 4. So every time, at any time, her acceleration is 4. And in this case, we will say that if we are going up in miles per hour, she probably wouldn't be accelerating so slow that she would only go up 4 miles per hour every hour. I'm going to say it's seconds. You'll probably be given these units in the typed up questions that you're facing on your homework or on the AP exam. Units will be more clear, but this would make sense, whereas miles per hour squared would not really make sense. The last thing that I want to bring up to you is about free fall. Okay, when they talk about objects that are thrown into the air or dropped or anything like that, or something jumps up and comes down, we'll think about the position over time, the distance over time as an upside down parabola. Whether or not they tell you, there are things that you do know, okay? When an object is at the top of its arc, the velocity is 0, and that makes sense. If velocity is our derivative, we know that the derivative, the slope of the tangent line, at the top of a parabola is 0. And so we know the velocity is 0 if we're talking about the maximum height that that object reaches. And we also know, like we did in that first problem, that when it hits the ground, the distance is 0. The distance from the ground is 0. So even though they don't necessarily tell you those sometimes in the word problems, you do know those two things, and you can use those two pieces of information to help you out. So if they, say something about the maximum height that it reaches, you know that at that time the velocity is 0. So that could help you out setting things up. And that concludes this lesson for now. We will revisit this in a few weeks.